Welcome back, everybody, for another deep dive.
Oh, it's exciting to be back.
And today we're looking at the optimization of wireless networks.
Oh, yeah.
Specifically 5G and beyond into 6G.
Okay.
And we have some pretty cool stuff to go over.
Yeah.
We have academic research papers. We have industry white papers.
Right.
And we even have some documents from something called the IOWN Global Forum.
Interesting.
They're working on the future of networks.
Cool.
So by the end of this, I hope we'll both be experts on digital twins.
Well, that's what's so exciting about this research is that these are actually like real-world applications impacting how networks are designed and managed today.
Okay, cool. So let's start with this digital twin idea. It sounds very futuristic to me.
Yeah.
But what exactly is a digital twin?
So think of it as a virtual mirror image of the physical network, a digital replica that allows engineers to simulate, analyze, and optimize every aspect of the network.
So like a giant sandbox where they can test out different configurations and strategies without messing with what people are using.
That's a great analogy and incredibly important when we think about the explosion of data and the complexity of 5G networks. Optimization is a huge challenge, and digital twins are a powerful tool to tackle that.
Yeah, and one of the papers that you shared was about how they're using digital twins to optimize the interplay between 4G and 5G networks with things like dynamic spectrum sharing and dual connectivity. It got a little technical for me.
Yeah, it can get pretty complex. But essentially, these are techniques used to maximize the efficiency of the radio spectrum. So dynamic spectrum sharing, DSS, allows both 4G and 5G to share the same frequency bands. It's like having a two-lane highway, but instead of cars, it's 4G and 5G traffic sharing the road.
Right.
And then you have dual connectivity, DC, which allows devices to connect to both 4G and 5G at the same time.
So making the most of those limited airwaves.
Yeah, exactly. And the research actually showed how digital twins can be used to analyze the impact of allocating a portion of the 4G spectrum to 5G. They looked at what happens when 25% of the 4G band is given over to 5G traffic, using both DSS and DC.
So they're running the scenarios and finding the best way to share without impacting 4G users.
Yeah.
Clever. How do they actually build a digital twin, though? That accurately reflects the real world.
Well, building a digital twin is fascinating. And one of the papers breaks it down into three key components: the mirror model, the simulation model, and the integration model.
Okay, so the mirror model is...
The mirror model is all about real-time monitoring. So it's like having a live stream of data flowing from the real network into the digital twin. And this includes things like network traffic, signal strength, user locations, all sorts of key performance indicators.
So a constantly updated snapshot of what's happening.
Precisely. And all this data feeds the simulation model.
That's where the real magic happens.
Exactly. The simulation model uses that real-time data to run what-if scenarios. What happens if there's a sudden surge in traffic? What happens if a base station goes offline? Predicting how the network will behave.
Under different conditions.
Yes.
And so that's how they test out different optimization strategies before implementing them. Okay, and the integration model.
The integration model is the glue that holds it all together, connecting the mirror model and the simulation model, creating this feedback loop where the digital twin is constantly learning, and then uses that knowledge to make better predictions and optimizations.
A self-learning system.
Exactly, and that's where things get really interesting. One of the research papers gave a great example: an AI-powered sleep mechanism for base stations. So this AI system can analyze real-time traffic patterns. If it sees that traffic is really low in a certain area at night, it can put some of the base stations to sleep, saving energy without impacting service.
Sleeping base stations, I love it. This makes me think about how, I was in the middle of a really important phone call once, and the signal just dropped, and it was so frustrating.
Yeah, we've all been there. It's easy to forget how complex and delicate these networks are, but it's amazing to think that these digital twins are working behind the scenes to keep everything running smoothly.
Yeah, keeping those disruptions from happening. So we talked a lot about this digital twin thing. Let's move on to some of these new transceiver technologies. The future is calling.
Absolutely. Well, one of the research papers that you sent me highlights three really exciting technologies: reconfigurable intelligent surfaces, or RIS, flexible antennas, or FA, and holographic MIMO, or HE-MIMO.
Those all sound pretty sci-fi to me. Let's start with RIS. What is that all about?
Okay, so imagine a surface that can actually manipulate radio waves. That's basically what an RIS is. They can be strategically placed in the environment, on buildings, for example, to improve signal strength and even bypass obstacles.
So like a force field for radio waves.
Yeah.
Bending them around things that would normally block the signal.
Yeah, that's a great way to think about it.
Incredible.
Then you have flexible antennas, or FAs. These antennas can actually adjust their position to optimize signal transmission.
I'm picturing like a sunflower that's always turning to face the sun, but in this case, it's turning to get the best possible signal.
Exactly. It's all about adaptability, especially in these complex and ever-changing environments.
Okay.
And then there's holographic MIMO, or HMIMO. That's where things get really mind-bending.
Okay, hit me.
HMIMO uses a massive number of tiny antennas packed very closely together to precisely control the electromagnetic field. It's like having a super focused beam of radio waves.
Oh, now you're talking like tractor beams and sci-fi. But what's interesting about these technologies is that they're not just about improving signal strength or data rates. It's about understanding the semantics of the data.
That's a great point. Yeah, it's not just about sending bits and bytes anymore. It's about understanding what that data means.
So if a self-driving car is sending a message to other cars about its intentions, that data is pretty important.
Absolutely. These next-gen transceiver technologies are being designed with that kind of semantic awareness in mind.
Okay.
So your self-driving car's messages will always get through, even if someone's streaming cat videos in the back seat.
So we've talked a lot about these digital twins and futuristic transceivers. Are they actually being used in the real world?
They absolutely are. We have some really cool examples of real-world digital twin platforms in these materials that you sent me.
Awesome.
The one that really stands out is called Coliseum. It was developed by researchers at Northeastern University, and it's specifically designed to emulate real-world wireless environments using something called software-defined radios, or SDRs, and specialized chips called FPGAs.
Can you break those down a little bit?
Yeah, basically these SDRs and FPGAs give Coliseum the flexibility to mimic a wide range of network equipment and scenarios, creating a virtual network that behaves just like a real one.
Okay, so what can they do with this Coliseum thing?
One really cool thing they can do is recreate real-world scenarios from actual cities. The research mentions that they can emulate environments from Tokyo, allowing researchers to test their innovations in a very realistic setting.
So they built like a virtual Tokyo and tested new networks.
Exactly, a digital twin of an entire urban environment.
That's incredible.
But Coliseum isn't the only example. While Coliseum provides this controlled testing environment, researchers are also developing techniques to build digital twins directly from real-world data. One fascinating approach is called passive channel sounding.
Passive channel sounding.
So think of it like this: listening to the echoes in a room to understand its shape and size. But instead of sound waves, we're talking about radio waves.
Okay.
So by analyzing the existing radio waves in the environment, they can build a picture of the network.
Interesting.
Exactly. And the research shows that these digital twins can predict electromagnetic field strength with remarkable precision.
Okay, so how is that useful?
What allows network operators to precisely place and optimize antennas in 5G networks. By understanding the electromagnetic field strength at different locations, they can fine-tune antenna placement to get the best coverage and signal quality.
Squeezing out every bit of performance.
Precisely. Now, it's important to remember that these digital twins aren't just limited to optimizing wireless networks. The applications are much broader than that.
I was just thinking that. What other things are they being used for?
Well, one of the documents from the IOWN Global Forum that you provided explores all sorts of uses, everything from improving network resilience to reducing energy consumption, and even preparing for black swan events.
Those are the unexpected events that can really mess things up.
Exactly. And the document talks about how digital twins can help model and prepare for those unexpected scenarios, like natural disasters or major power outages. They can run simulations to see how the network would be affected, and then come up with strategies to minimize the impact.
So not just efficiency, but also resilience. Very important.
Absolutely. But it goes beyond just disaster preparedness. The document also highlights how digital twins are being used to design smarter cities.
Oh, no, that's interesting to me. Tell me more about that.
Imagine a digital twin of an entire city, complete with all its infrastructure, transportation systems, energy grids, everything. They can simulate traffic patterns, experiment with new energy-saving measures, even model the spread of diseases.
So like a network digital twin,
Yep.
but scaled up to an entire city?
Exactly.
What were some of the examples that they gave?
One really interesting concept they highlight is something called green twins.
Green twins.
So these are digital twins that combine data from different sources, transportation buildings, energy grids, to optimize energy use across the entire city.
Cool.
It's all about creating a more integrated and sustainable urban environment.
It sounds like they have the potential to transform a lot of things. Are there any challenges with these digital twins?
Of course, no technology is perfect. Some of the key challenges that the documents highlight include the need for robust data collection, making sure different systems can talk to each other, interoperability, and ensuring the security and privacy of sensitive information.
Those are all very important.
Absolutely. One of the documents uses the example of a platform for simulating and visualizing complex urban environments. And it really emphasizes the importance of addressing those challenges to unlock the full potential of digital twins.
Yeah, you need to have a good foundation. This is pretty mind-blowing stuff. It seems like digital twins are no longer a futuristic concept, but they're already being used in some really innovative ways.
Exactly. We've covered a lot of ground today. From the nuts and bolts of digital twins to their potential to reshape our world, it's really quite remarkable.
Yeah, it really is remarkable. So